Welcome to this explainer. Today, we're tackling an absolutely massive hurdle in modern tech, and that is, how do we actually teach artificial intelligence to interact with our physical spaces? Look, we all know AI can write code, it can generate amazing images, but getting a robot to reliably pour a cup of coffee or, say, fold your laundry, that is a completely different ballgame. It requires a totally different kind of understanding. So, let's dive right into the core problem. There's a quote from a recent breakthrough paper that hits the nail on the head. Basically, an AI reading text or analyzing pictures is actually pretty straightforward because, well, it can just consume the whole internet. But an embodied agent, meaning a physical robot, doesn't get that shortcut. A robot needs data that directly links visual observations with physical states. We're talking weights, friction, precise motor actions. And the internet just doesn't naturally provide that kind of physical grounding. That brings us to the crucial point we are exploring today, this fundamental trade-off. On one side, we've got scalability. This is our ability to gather massive amounts of data efficiently, with very little human labor and low cost. But on the flip side, we have robot alignment, which is how directly that data actually supports execution on a physical robot. As it turns out, finding data that scores high on both of those metrics at the same time is incredibly difficult.
To break this complex topic down, we're going to follow a clear path today. First, the robot learning problem. 2, the embodied data pyramid. 3, top layers, robot and UM. 4, mid layers, ego and sim. 5, the base, general data. And finally, 6, the future of robotics. We're going to travel from the top down to see exactly how we are training the robots of tomorrow.
Okay, Section 1, the robot learning problem. Let's look at exactly why robots struggle to learn from traditional internet data. There was a massive collaborative study involving some top institutions, and the abstract highlights a really critical realization. We need a completely new ecosystem of data sources. If we want to build next-generation embodied systems, we literally have to move beyond just vision and language data. We need a systematic way to organize how we collect and use physical data to train models in perception, planning, and world prediction. Moving on to Section 2, the Embodied Data Pyramid. Here is the researchers' brilliant solution for organizing all this information. This comprehensive overview categorizes the whole embodied data ecosystem into a really neat 5-layer pyramid. Starting on the far left at the apex, we have robot data. Then we descend through UMI, ego, simulation, all the way down to general data at the base. But to really grasp how this operates, you have to look at the adjacent columns. The layout section details exactly how this data is gathered, building from broad cognitive and perception data at the very bottom, up to environmental data in the middle, and finally relying on explicit capture infrastructure at the top for specific tasks. Moving right, the applications column shows how this data is practically used to train embodied brain models and world action models. This is what determines exactly how a robot thinks and moves. And finally, the trends column points us toward the future, mapping out ongoing challenges. Things like cross-embodiment alignment, unified perception, and large-scale tactical data sets. It is a complete, beautifully structured roadmap to help researchers navigate a massive sea of data. Now, as we step down this pyramid, keep in mind that the whole structure is governed by those two primary axes we talked about earlier, scalability versus robot alignment. And as the graphic points out, these axes are very often in intense tension with one another. Moving down the pyramid means we are actively trading direct physical robot supervision, which is incredibly hard to get, for massive accessibility and scale. It's a deliberate sacrifice of hardware accuracy in exchange for sheer data volume, diversity, and reusability.
Section 3, top layers, robot and UMI. Let's look at what researchers consider the absolute gold standard of data.
Sitting right at the apex is real robot data, and it is exactly what it sounds like. It's a human teleoperating a robot, or a script running directly on the target hardware. Because it records everything in a closed loop, meaning it captures what the robot sees, how its joints are positioned, and the physical outcome of its action, it is highly aligned and immediately executable. But there is a catch. Nothing is more expensive. Every single hour of data requires actual hardware, human operators, and manual environment resets. It is notoriously difficult to scale up. Stepping down just one layer, we find UMI, or Universal Manipulation Interface data. This is honestly an ingenious workaround. UMI-style data drops the bulky, expensive robot from the collection process entirely, Instead, humans use portable, robot-free interfaces. Think handheld camera rigs that track hand movements, while keeping a really explicit focus on how the gripper or end effector moves. This drastically lowers costs and lets us collect data out in the wild, all while maintaining that crucial structural supervision of how a hand interacts with an object. Moving to Section 4, Mid-Layers, Ego and Sim. This is where we start scaling through diversity. Now we are entering the realm of human video data. On the left, we see an egocentric or first-person perspective of hands interacting with a milk carton and a coffee machine. It captures those natural, high degree of freedom hand motions perfectly, but the hands often block the view. That's exactly why we pair it with the exocentric view on the right. That static room camera ensures the human body doesn't include the wider environment, giving the AI a complete, uninterrupted record of the action. This kind of human video data gives us highly scalable, authentic street smarts by capturing humans in diverse, in-the-wild environments. Just like these living rooms full of couches, plants, tables, and everyday clutter, we get incredible task diversity. But there's a major challenge here, known as the embodiment gap. See, we have massive amounts of data showing a human body doing a task, but translating those human joints and muscles to the rigid hardware of a robotic arm, that is mathematically and physically complex.
So to solve those hardware mapping issues, we move to simulation data. By sequencing frames of cyan, gray, and red blocks colliding, simulation allows us to generate infinite, perfectly labeled scenarios inside a physics engine. It's amazing because we can automate the collection of finely segmented behaviors, and we have absolute, total control over the environment.
The big takeaway here is that simulation forms the most scalable and cost-efficient robot-aligned layer. It's fantastic for dense, controllable supervision. However, robots that are trained perfectly in simulation often struggle terribly when deployed to the real world. Why? Well, because the physics engine is just an approximation. Simulated materials, object interactions, and the subtle friction of real-world surfaces are never quite perfect. It creates this reality gap that our models have to overcome.
Section 5. The base. General data. Let's look at how we build the semantic foundation.
Down at this bottom layer, we abandon robot physical grounding entirely. Instead, we go for massive semantic knowledge and spatial reasoning. Essentially, we are giving the AI its book smarts. On the left, the system is identifying an eraser next to a coffee mug with a 2D bounding box. And on the right, it's projecting a 3D bounding box to locate a speaker tucked under a desk in a highly cluttered room. This is how we teach the model the geometry and spatial awareness it desperately needs to navigate.
General data also includes complex vision language tasks. For example, analyzing a vintage envelope from 1970. The AI uses optical character recognition to read the handwriting and actually identify the zip code as 80202. Before a robot ever even attempts to move its mechanical arm to, say, sort your mail, it absolutely must possess this cognitive foundation so it understands what it's even looking at.
Furthermore, by absorbing millions of images of everyday environments, like these unstructured living spaces featuring refrigerators, TVs, scattered papers, and decorative items, the model learns broad, common-sense reasoning. It learns what items belong in a kitchen versus a living room. It learns where a handle is typically located on a fridge. It learns how everyday objects relate to one another semantically. Finally, Section 6, the future of robotics. Let's see where we go from here. Take a look at how this all builds over time. The timeline chart we're looking at is honestly staggering. If you track across every single vertical, starting from simulation data on the far left, moving through UMI, robot, ego, and finally general data on the right, we are witnessing explosive, exponential growth in recent years. Look closely at the robot data column. The orange trend line shows these massive spikes, literally climbing up to 4.19 million demonstrations. In the simulation column, you can see similar aggressive upward curves as simulated parameters scale up. And then the general data column on the far right reveals datasets hitting billions of images and parameters. What this detailed breakdown proves is that researchers aren't just relying on one layer anymore. They are actively mixing and matching these data recipes. They're blending the raw volume of general data with the extreme precision of real robot data to train incredibly smart foundation models. But, the job isn't quite done yet. The research community still faces 6 massive open challenges. We need to develop scalable collection pipelines, align actions across different robot bodies, leverage egocentric data for dexterous manipulation, and design principled data recipes. The final 2, though, are perhaps the most pressing. First, building large-scale tactile datasets. We literally have to teach a robot how to feel touch and pressure. And second, collecting failure and recovery data.
Right now, most of our datasets show perfect execution, but a smart robot needs to know what to do when it drops the cup, right? It needs to recognize its own failure and know how to recover gracefully without a human having to step in.
So I want to leave you with this provocative thought. We are rapidly scaling this embodied data pyramid. We are actively solving the translation between digital intelligence and physical hardware. Once we overcome this massive data hurdle and finally give AI a reliable, adaptable physical body, what does our day-to-day life actually look like? When robots finally have the street smarts and physical dexterity to exist safely in our homes, how will they reshape the everyday spaces we live in? Thank you so much for joining me on this explainer, and keep exploring the incredible world of embodied intelligence.